All right, everybody, welcome back to the last section here of the semester. So we're going to be talking about inverse matrices today, and we're going to tie it back to our original conversation about solving systems of equations using matrices, or systems of linear equations. And so first, let's talk about what this guy called the identity matrix. So an identity matrix is a square matrix. It has the same number of rows as it does columns. And it is given by the matrix that has ones along the diagonal and zeros everywhere else. So let's just see what we mean by that. There's one for each kind of size, n by n. So I left off the first one here. I1 would just be the single number 1. That's fine. And then the sort of 2 by 2 identity matrix, which I'll write as I sub 2, that is this matrix here, whose first row, first column entry is 1. Its second row, second column entry is 1. And every other entry is 0. So that's this diagonal here. The 3 by 3 identity matrix is the matrix whose first row, first column entry is 1. Its second row, second column entry is 1. Its third row, third column entry is 1. And every other entry is 0. Okay, etc., etc. And so we have like, what I mean by etc. is that we have one for 4, 5, 6, etc. Okay. Okay, so then let's do some multiplication. Let's multiply some matrix by an identity matrix. So here we have this 2 by 2 matrix whose rows are 7, minus 2, and minus 3, 5. And we'll multiply it by I2. So the first row, first column entry of the product is given by the first row of this matrix, I'll call it A, times the first column of this matrix I. And so that gives us 7 times 1 plus minus 2 times 0. That is 7. The first row, second column entry of the product is given by the first row of A times the second column of I. So that gives us 7 times 0 plus minus 2 times 1. Okay, that's minus 2. Then the second row, first column entry of the product is given by the second row of A times the first column of I. That gives us minus 3 times 1 plus 5 times 0, which is minus 3. And then the second row, second column entry of the product is the second row of A here times the second column of I. That gives us minus 3 times 0 plus 5 times 1. That is 5. And notice that this product is the same as the matrix that we started with. So multiplying by an identity matrix didn't change the matrix that we started with. And so this is the kind of key here, is that identity matrices behave like the number 1 does in terms of multiplication. Remember I said that I didn't write it here, but I sub 1 is a 1 by 1 matrix whose only entry is the number 1. It's the number that when you multiply any other number by 1, you get whatever you started with back. Right? So it's the number that multiplication doesn't do anything, right? And so, okay. So then an inverse matrix works as follows. So let's let A be an n by n matrix, and let's let I sub n be the identity matrix of size n by n. Then if there's another matrix, which we would write as A inverse, that satisfies the property that A times A inverse equals I sub n, and A inverse times A equals I sub n, we say that A inverse is the multiplicative inverse of A. Okay? This is just like if you have a number and you want to find its reciprocal. Okay? So say you have the number 3 or something like that. Then 3 times 1/3 equals to 1. And 1/3 times 3 equals to 1. So 1/3 is what they call the multiplicative inverse of 3. Okay, so in some sense, it's like this is kind of asking us about, can we divide by a matrix in sort of air quotes? And so it's not always possible to do this, right? And think about it with numbers too. There's a single number that does not have a well-defined reciprocal. The number 0 does not have a multiplicative inverse, as they'd say, because 1 over 0 is the only thing it would morally be, and that is an undefined nonsense number. So, okay. So they're going to give us an example here to show that these two matrices given here are inverses of each other. And this is a little bit like just kind of a routine check. So if you multiply the first matrix by the second one and show all your little work there, you will get back that first product is the 2 by 2 identity matrix. And if you interchange the order of the two and multiply them the other way, you'll still get back the 2 by 2 identity matrix. So in fact, these two are inverses of each other. Okay, so I'm going to skip all the kind of details of this example because it's a little bit less fun than the procedure for if we're just given some matrix that we know has an inverse, or that maybe Connect Math tells us has an inverse or something like that. And we want to find what that inverse matrix is. Then there's a nice little procedure that works kind of very similar to our Gauss-Jordan elimination work. So we'll first make an augmented matrix for our guy, where our guy A is on the left side of the bar, and then the identity matrix that we have for that size is on the right side of the bar. And then we will use elementary row operations to change the left side into the identity matrix I sub n. And as we do that, we will ultimately change what's going on the right side as well anytime we're doing those row operations. And so we'll get some new thing on the other side at the end, and that new thing will be A inverse. So let's watch it go here. So we start with this matrix whose rows are 5, 7, and 3, 4. And I'll set up this augmented matrix here. And I would like to turn the left side into the 2 by 2 identity matrix. So namely, I would like this first entry up here to be 1 instead of 5. So I can do that if I multiply the whole first row by 1/5. So that gives me a new first row of having 1 and 7/5 on the left side of the bar, and 1/5 and 0 on the right side of the bar. Okay. Now that I have that 1 up here in the top left corner, I would like the number beneath it to be 0. And I can do that if I subtract 3 times the first row from the second row. So in other words, I will replace the second row with the second row plus 1/3 times the first, or sorry, plus -3 times the first row. Okay, so then doing that gives me, in this first entry down here, I have 3 plus -3 times 1. Well, that's 3 minus 3, which is 0. And I also have 4 plus -3 times 7 over 5. So that should give me -1 over 5. Okay. Then I'll also have 0 plus -3 times a fifth. That gives me 0 minus 3/5, which is -3/5. And I'll also have 1 plus -3 times 0. Well, that should just be 1, because 3 times 0 is 0. Okay, so now that I've got this first column taken care of, I'd like to go to the second column. And I want it to have a 1 in the bottom entry and a 0 above it. So first I'll get that 1 there by multiplying the whole second row by -5. Okay, so 0 times -5 is still 0. -1/5 times -5 is 1. That's nice. -3/5 times -5 is 3. That's very nice. And 1 times -5 is -5. Ah, very nice. Okay, so now that I've got this 1 here in the bottom left, I'd like the number above it to be 0. And I can make that happen if I add -7/5 times the second row back to the first row. And so doing that gives me, I'll keep 1 in this first row, first column entry here, because 1 plus minus 7/5 times 0 is still 1, because minus 7/5 times 0 is 0. Okay, but then this entry up here becomes 0 as we start with 7/5 and add to it minus 7/5 times 1. That is 0, okay, when you add them together. And then we'll have here 1/5, and we will add to that minus 7/5 times 3. That gives us minus 21/5 plus 1/5 is minus 20/5, which is minus 4. And then last here we have 0, and we're going to add to that minus 7/5 times minus 5. Well, that will be then 0 plus 7, which is 7. Okay, and so now we've got the 2x2 identity matrix on the left side of this equation, or on the left side of this augmented matrix. And we've got this new matrix on the right side of the augmented matrix. And this new one is A inverse. And you can check that in the comfort of your own home. All right. And so maybe we might want to compare at this point, is there any kind of relationship between the numbers in the matrix A and the numbers in the inverse matrix? It looks to me like they're kind of almost all the same numbers, except maybe the order has been jumbled up a little bit, and maybe there's been some minus signs introduced, right? It looks like the relationship between, well, it looks like we really interchanged the 4 and the 5, right? And then they also became minus. Okay, well, there's something a little bit deeper going on there with that, or maybe not deeper, but quicker, actually, going on with that we will discuss in the next slide, in the next video. So we'll see you then.